choose 4, 5, 6.
Look at the graph. So you want to disconnect to 3 and connect the first vertex. So you choose always the first vertex and connect it to somebody else.
Okay.
So 2 cannot be connected again to 3 and you cannot connect it to 1 because it's already connected. So in this network the candidates are just 4, 5 and 6.
Okay, got it.
Okay. So that's why, so each one has equal probability, so you have this individual probabilities and cumulative probabilities. Then what you do? Generate again a random number. So in my case,
my question is through 2, like if you go through 1, then you can get the another 6, right?
No, I want to decide whether 2 should be connected to 4 or 2 to 5 or 2 to 6. I want to connect like this.
Okay.
Okay, that's called rewire.
Okay.
Okay. So I generate a random number, so I get 0.422. So how we follow the convention? Find the largest and closest. So 0.422 falls between these two cumulative probability values. So which one should get that link? 5. 0.67 is the closest and largest. So it means at the end of this process, of the first rewiring process, 2 is connected to 5. So the network has changed from this to this. Is that clear? So we still have 2 more edges to consider for rewiring, 3, 4 and 5, 6. We'll repeat the same process. Look at 3, 4, the new network. So 3, 4 is like this. So we want to disconnect 3, 4. We don't want to bring that previous link that we removed back. So which means when we look at the candidates with which 3 can be connected to, we should not consider 2 as a candidate node. Because considering that will bring back that H2, 3. We don't want to do that. So the candidates are, like we cannot look at 4, we cannot look at 2. So it's either 1, 5 or 6. Those are the 3 candidate nodes with which 3 can be connected to. Yes?
So when we are disconnecting, so first we took 2 and 3, and after that 3 and 4. So can we take?
You can take the other way also, it's fine. It doesn't matter. Okay? We just follow the convention, like the lower ID edge first and so on. Okay? Doesn't really matter the order you do. So the candidates are 1, 5 and 6. Again, they have equal probabilities, so the cumulative probabilities as usual. Now the random number I generate is 0.665, so which is going to be less than or equal to 0.67. So the node with which 3 is going to be connected is 5. So at the end of this process, we're going to get 3, 5. Okay, so this is the edge. So now the last pair is 5, 6. So we're going to disconnect 5 and 6. So now you see 5 is already attached to 2, 5 to 3, 5 to 4. So you want to find a pair for 5, right? Because that's the first vertex. So the only candidate could be 1 because 5 cannot be connected back to 6. It's already connected to 2, 3, 4. So you don't have to really generate any probability. 1 is the only node with which you can connect to. Okay? So any random number that you generate is going to be less than or equal to 1. So it's going to be an edge between 1 and 5. Okay? So at the end, what will happen after this 3 rewiring process? So I show the transformation of the graph. So this is the final network. Okay? So we can cross check. Of course, this is a small graph, so some properties may not have changed as you expect. But let us see. You can try to find the average path length. So how to get the average path length? Get the distance matrix between any 2 vertices, right? The distance is what the number of edges on the shortest path. Then sum up all these numbers, the distance matrix, excluding the zeros, and divide by the number of paths that you have. We did this before for average path length, right? So sum up all these numbers. 1, 2, 3, 2, 1, then 1, 1, 2, 3, 2, sum everything other than 0 in this matrix. Divide by the number of entries we have. So you have 6 vertices, and each row you counted 5 values, 5 non-zero values. So the sum divided by 6 times 5 will give you the average path length. Is that clear? So repeat the same process on this network. Find the path length between any 2 nodes. Add the this up and divide by the number of pairs, you will get 1.73 for this and it is 1.8 for this one. So the path length has reduced a little bit. That's what we expect to see, right? By doing this transformation of a regular network to a small world network, we want to reduce the path length. Okay? And it has happened. Of course, it need not have happened because it's a very small network, but for a very large network, you do expect to reduce the path length with this process. Is that clear? Okay. Now, the clustering coefficient would have also reduced. Okay. So let us look at that as a formula first. So there's a formula for a regular graph with each vertex having a degree k. This is the formula for the clustering coefficient. So C of 0 means it's a regular network, alright? We don't rewire any link, isn't it? So if beta is 0, it means a regular network. So C of 0 means say of beta is 0 for a regular network. This is the formula for the clustering coefficient. Then as you go through the transformation process by doing rewiring, the formula for the clustering coefficient as a function of beta is going to be C of 0 times 1 minus beta the whole cube. So this is the formula for the clustering coefficient as a function of beta. Okay, so a function of the rewiring probability. Is that clear? So if you plot this function, okay, so just keeping this as a constant, okay. I think I have used some numbers, let me check. K equals 4. Yeah. So let us use K equals 4. This is a ring network with say 4 neighbors for each node and 20 nodes. Okay. The number of nodes does not really matter. So if you look at the formula, it is a K that is accounted for here. So C of 0, the initial clustering coefficient is 3 times 4 minus 2 divided by 4 times 4 minus 1. So if you simplify that, it is 0.5. So that's the clustering coefficient for this regular network. Okay. So now what you do is substitute for different values of beta. So this is C of 0 is 0.5. Now as you increase beta, the clustering coefficient is going to reduce even further. So how it's going to reduce? According to this function. So if you try to plot it and visualize it, this is how it will reduce. When beta is 0, the clustering coefficient is 0.5. Now as we increase your beta, the reduction is what? As a function of beta. So it is C of 0 times 1 minus beta the whole cube. Now as you can see, for smaller values of beta, like 0.1 or 0.2, the reduction is not that much. Whereas as you increase beta, it reduces more drastically and approaches 0. So that is why we should not increase beta too much. If beta is 1, it corresponds to what? A random network. And for a random network, the clustering coefficient is expected to be very small. Okay? So that is why we scale with smaller values of beta. And that itself is good enough to rewire the edges in such a way that we have lower path length also. Okay? Any questions so far?
So Doug, after rewiring the graphs, from one graph you can have different kind of graph, or the graph is going to be the same thing but the random value is different?
The graph is going to be different. So we started say with this graph, went through the rewiring process and eventually ended up with this graph.
Yeah, now you choose a different number, right? If I use different random number, the
Yeah,
graph is
so
going to be the
yes.
same thing or it's just going to be
You're
different?
going to get a different graph. So if I assign this graph to all of you, there's no guarantee that everyone should end up with this graph. Each one could come up with a different graph. So that's what I said in the beginning. Okay, so it depends on the random numbers. So when you show your work, make sure you generate your own random number and decide which edges get rewired. So don't try to copy from others. I can easily find from this. Don't try to say both got the same random numbers. It's not possible at all. The probability of that happening is less than 1%. Okay? Less than 0.0001%. so now coming to an implicit problem, we have a numerical problem here. Let me check. Yeah, so this is just a workout of the clustering coefficient values. Now the path length. Okay, so another formula. For a random network, we know this formula already. The average path length is given by the logarithm of the number of nodes divided by logarithm of the average degree. Okay. So here we start with what a k regular graph. So with k equals 4. So we can use that as the average degree and find what is the average path length in the random network. For a regular network, the formula for average path length is very simple. It is n over 2k. Because as I said, you have to cross between, like go through all these edges and go to the other side. Okay, so like half of the network you have to travel. So n over 2k. So if you have more neighbors for each node, you would save the distance. If you have fewer neighbors, just like this in a ring, what do you have to do? You have 6 nodes. To get between like this node and this node, you have to go through 3 edges, like half of the network. And if you increase, like if you had more nodes and still keep it regular, you are going to reduce the path length. Okay, so that's why it's n over 2k. So 20 divided by 2 times 4 is 2.5. Okay, so that's how we calculate the path length for a regular network and for a random network. Okay.
So that's the formula then? C beta.
This is the formula for clustering coefficient. Okay, so this is the formula for path length.
Yeah.
There's no path length. There's no formula for path length for a small word network because it all depends on probability. So it's not that easy to mathematically formulate like this for clustering coefficient, the path length. Okay, so now let us get into the weakness of this model. So again, how can this be used for modeling real world networks? So let us say you start with a real world network like this. Okay, it's like even the road example. Okay, so if I want to reduce the path length between any 2 street intersection, we agree that we have to rewire the roads such that we can have some long distance roads so that we can travel, I think, through fewer street intersections. But that doesn't mean that you will put a road from here, say, to a very far away place, say New York. You cannot run a long interstate from one stretch. You see what I mean? So you have an interstate to a nearby larger city, typically, right? So if I were to rewire in a more logical, common sense approach that is really practical enough, feasible, okay? If I want to rewire this H23, I want to remove this H23 and connect 2 to somebody else. According to our probability, this Watts-Rogarts model, we end up connecting what? 2 with 5. Okay? Which is like almost half of the network. You're bypassing like these 3 edges and you're just directly connecting 2 and 5. But if you want from a reality perspective, right, to the cost associated with implementing such a long distance edge, it's going to be much. So you would prefer to rewire like what? 2 with either 6 or 2 with either 4. Because these 4 is like 2 edges away from 2, 6 is also 2 edges away from 2. And 5 is what? 3 edges away from 2.
Same difference.
What same difference?
Like number of paths, it will take 3, and on that side also it will take 3.
3, yeah. So 5 is 3 edges away from 2, right? Whereas 4 and 6 are 2 edges away from 2. So the motivation is now, see in the previous case, what did we do? Once we decided 4, 5, 6 were candidates, we assigned equal probability, 1/3, 1/3, 1/3, and then went about deciding which one to go for, and we ended up with 5. So now what we want to do is, we want to give more preference for nodes that are closer. Okay, so more larger weight for nodes that are closer, and lower weight for nodes that are farther away. Is that clear? So that's the idea behind what's called the enhanced Watts-Rogarts model. Okay, so we're going to see an enhanced.
So
model.
once again, how 5?
Do you remember the example that we went through? So we started with this network, decided to rewire the H23, So when you remove the edge 2, 3, what's going to happen? You want to decide who to attach to 2. So we cannot connect 2 back to 3 or 2 to 1.
Yeah.
So you have to decide among 4, 5, 6.
Yeah, and 4,
That
5,
was an
6,
equal
5, 5.
probability, and we end up with 5. But this approach led us to what? Decide, put a long distance edge between 2 and 5.
2 and 5.
Right?
Yeah.
Because you see, according to the regular graph given to you, there are 3 edges apart from each other.
Yeah.
Path length between them is 3. So if you want to really connect them like this, in
It will
reality
take
it's
too
going
time.
to take much cost and all the effort. So we don't want to, okay, we want to rewire, but doesn't mean that we could randomly rewire to some distance vertex. We have to rewire to a vertex that is relatively closer. Okay, so we want to give more preference. Okay, again, still a probability. So vertices 4 and 6 will have a higher probability of getting that edge to 2 compared to vertex 5.
5.
Okay, so that's what we're going to see in the enhanced model. Okay, so it's called the enhanced Watts-Rogers model, and we're going to see a couple of examples for that. But what is that probability? Okay, so that probability was the same for before the Watts-Rogers model. Enhanced version, as I said, the probability is a function of the distance between the nodes, right? So smaller the distance, higher the probability, right? So this distance is going to be the denominator. So the formula is like this. I don't have a good marker. So it's like distance between the 2 vertices times 1 over 2 log n. Okay. So again, the larger the number of nodes, the lower the probability. So this is the probability now. So if you, as you can see, if I bring this to the numerator, it's going to look like what? D distance from U to W raised to negative Q. Is that clear? So what is this Q? The Q is the dimensionality of the network. Remember, start with a regular network and change it to a small world network, right? So for regular network, I said the dimensionality is also a parameter to be considered. So if it's a ring, the dimensionality is 1. If it's a lattice, the dimensionality is 2. So regular networks have some dimensionality. Okay, so Q is like integer 1, 2, and so on. So let us see the simulation and then come back to a small problem. I just want to keep continuing. Okay. So how to go through this rewiring process with the enhanced model. Okay. So this is a lattice given to you. So the Q is 2. Okay. So the first step is to generate a distance matrix. Okay. So you have all vertices. So find the distance between any 2 vertices. Okay. So square is a symmetric matrix. So just fill the upper diagonal. So that's good enough. Okay. So then what you do, using this function, try to generate the weights that you want to give to the distances. So as I said, you don't want to give equal weights. You want to give more larger weight for nodes that are closer to the vertex and lower weight to vertices that are farther away. So from this distance matrix, identify the possible distance values you have for this given graph. The distance values are 1, 2, 3, and 4. So those are the distance values that are possible that are in this graph, right? So for those distance values, generate the weights. So what you do, the distance of 1, the formula is d to the power negative q divided by 2 log n. So n is the number of vertices, so it is 9 here. So you would do something like what I showed. For distance of 1, 1 raised to negative 2 divided by 2 log n, 2 log 9. So 1 raised to negative 2 is 1 divided by 2 log 9. So the probability came up to be some, not the probability, the distance, the weight. So the weight came up to be 0.524 for a distance 1. For distance 2, what would you do? 2 to the power negative q divided by 2 log n. So what is q again? Q is 2. So it's 2 to the power negative 2 divided by 2 log 9. So that will give you 0.131. So I have shown the work here. Okay. Then for distance 3, it's going to be what? 3 to the power negative q, which is 2 divided by 2 log n, 2 log 9. So that's going to be 0.058.
So Q means what?
Q is the dimensionality. So since this is a lattice, the
Yeah,
Q is
2 dimension.
2 dimension. Then for a distance of 4, the weight to be given is 4 raised to negative q divided by 2 log 9. Okay, so as you can see, these are the weights. Okay, so in the previous case we said we'll equally consider equal weight. So now we are giving more weight to nodes that are within one distance, one edge away from each other, and very less weight to nodes that are 4 edges away from each other. Is that clear? So that's the distance-based weight. So from the distance matrix, we can also find out the pairs that are at such a distance from each other. So for example, 1 and 2 are 1 edge away from each other. Okay. Similarly, 1 and 4 are 1 edge away from each other. So write down all the pairs that are 1 edge away from each other. Similarly, write down all the pairs that are 2 edge away from each other. Okay. So 1, 3 is 2 edge away from each other, and so on. Okay. So these are all the pairs of vertices that are separated by a particular distance. Okay. So once we set up everything, we can decide to rewire any link we want. So let us say we want to rewire the edge 1, 2. So which means I need to remove this edge 1, 2 and connect 1 to some other vertex. Is that clear? So the candidates are, you cannot have 2 or you cannot have 4. So it has to be 3, 5, 6, 7, 8, 9. So one among the 6 vertices. Which means you can have an edge between 1 and 3. That's a pair now, but we can connect them, or 1 and 5, 1 and 6, 1, 7, 1, 8, 1, 9. Okay? So what we have to do? We have to find the probability with which the edge, the pair 1, 3 will get an edge. Or what's the probability the pair 1, 5 will get an edge, and so on. Okay? Based on our weights that we just computed. So these were the weights. So how to assign the weights? Look into that table, what's the distance for each pair. So 1, 3, of course you can look at the graph too. So 1, 3, the distance is 2. So the distance of 2, the pair 1, 3 is there. So the weight to be given for the pair 1, 3 is that weight corresponding to distance 2. So for each distance we computed the weights, isn't it? So for the distance 2, the weight is 0.131. So the pair 1, 3 gets that weight 0.131. Is that clear? Then 1, 5, the distance is also 2. So the pair 1, 5 also gets that weight 0.131. Then 1, 6, the distance is 3. So they get the weight corresponding to distance 3 and so on. So these are our distances. So now we want to make it like a probability. Okay, because the weights need not add up to 1, so we cannot go to the cumulative probability step right away. So what we have to do is we have to scale this up, or scale this weights. Okay, so one way to do that is add up all the weight values for these pairs. Yes.
In 1, 7, it should be 2, right?
Yes, 1, 7 is 2. So for 2, the probability is 0.131. So add up all the weight values, you get 0.542. Which weight values corresponding to these pairs? All the weight values the original weight values that you ended up for these pairs, add up all of them, you get this number. So then what you do? Divide each of these entries here by the 0.542. So that's what I mean by scaling the probability. So 0.131 divided by 0.542 is like normalization. Is 0.242. And similarly, this number divided by this, then 0.058 by 0.542 is 0.107. So why we did this? Because if you add up all these values, it will be what? 1. So these are like the probabilities with which these pair get that edge. Okay. So now we can go to cumulative probability approach. So the first entry is going to be the same as the individual probability. Second one is 0.242 plus this 0.242, so that is 0.484. Then this 0.484 plus 0.107 is 0.591. Then this number plus 0.242 is 0.833 and so on. So finally you should end up with 1. Is that clear? So then what you do? Just enter a random number. So in this case I get say 0.252 is my random number. So the closest and largest value is 0.484. So that means the pair 1, 5 are going to be connected. So it means I'm going to break this edge 1, 2 and connect 1, 5. So you see now the vertex 5 that was relatively closer to 1 gets the new edge. You did not randomly end up with like connecting 1 and 9, which are farther away from each other. Right? Because they are far from each other, so they have a lower probability for getting an edge. Okay? Whereas 1, 5 is closer to 1, so it has almost like 1/4 of the probability, 0.242 compared to 0.06 for 9. Okay? So this kind of, it is mimicking what is possible in reality. Okay? So if you have like a road network and you want to rewire the edges, you try to do this, and this will reduce the path length. Okay? It may not reduce as much as this, but this is really not that feasible to just put together two nodes that are very far away from each other. Is that clear? So you should show the work like this in an example. Okay? So I have another example, we can go through that. Okay, so I will give you the dimensionality. Okay, but if it is something more obvious like a ring, it is 1, or a lattice, it is 2. So we'll assume the dimensionality of this network is 1. Okay, so the Q is 1. So what's the first step? Given the graph, come up with the distance matrix. So just find the distance minimum edge paths, shortest paths between any two vertices. So then identify the distance values. So here we have 1, 2, or 3 as the distance values. So then what you do? Use that formula. So the formula is the distance raised to negative q, the dimensionality divided by 2 log n. So for the distance of 1, how would we get the weight? It's going to be the distance 1 raised to negative 1, the dimensionality, divided by 2 log 8. So it's still like 1 divided by 2 log 8 comes out to be 0.554. Then this is going to be for distance of 2, it's going to be 2 raised to negative 1 divided by 2 log 8. That is 0.277. For distance 3, it's 3 raised to negative 1 divided by 2 log 8. So these are the weights. So they need not add up to 1. So these are like some raw values. So now find the paths that are separated by the distance. So 1, 2, 1, 4, and all they have a distance of 1. Then 1, 3, 1, 5 also has a distance of 1, 2. Okay, so they all have distance 2. Then 1, 8 and 3, 6 are the only two pairs that have a distance of 3. Is that clear? Okay, so what I'll do is I could ask you to pick some random edge and rewire it, or I could ask like, okay, given the graph and the rewire and the dimensionality, okay, rewire the edge 1, 2 or 1, 4. So then you should rewire that particular edge. Okay. So let's see here. I say we want to rewire the edge 3, 5. Okay. So which means we want to remove 5. Remove the edge between 3 and 5 and rewire 3 to somebody else. Okay, so the first step is to identify the candidate nodes to which 3 can be connected to. So the candidate nodes are, you cannot have 2 and 5. Okay, so anything other than 2 and 5. So 1, 4, 6, 7, and 8. Right, so 3 connected to 1. Then 3 to 4, 3 to 6, 3 to 7, 3 to 8. So these are our original weight values based on the distances. So you need to know where, what's the distance between each pair. So 1, 3, the distance is 2. So use the weight corresponding to the distance 2. Okay, 0.277. 3, 4, the distance is Right, so then what you do, add up all the weights. So it could go even above 1, but if it scale it. Yeah. So 0.277 divided by 1.293 is going to be 0.214. Okay, then 0.185 divided by 1.293 is 0.143 and so on. So the sum of these scaled versions of probability should be 1. So then go through the cumulative probability process. Okay, and generate a random number. Let us say I get 0.9338 as a random number. So that falls here. So it is less than or equal to this number. Okay, so the H is going to be for what? The pair 38. Okay. So 38 or 2 edges away from each other. So it's more likely that that one got selected instead of 3 to 6. Okay. So 3 to 6 is going to be 3 edges that did not get selected. Is that clear? Okay. Of course, it's a random number based process. So if you get a random number that will choose 3, 6, it's fine. So don't think you made a mistake. But the chances of that happening is lower because as you can see the probabilities, the chances of 3, 6 to be chosen is 0.143, whereas the others have probability larger than that. Okay? Any questions so far? So now we have some small math problems that we'll try to finish off. So consider a regular ring lattice of degree 8 for every node. Okay, so we have a regular network of degree 8, and we need to transform this regular network to a small hole network by doing the rewiring with the probability beta, which is also given to be, no, we need to find the beta. So let the clustering coefficient of the resulting small hole network be 0.4. So what is given here? The regular degree is given, k is given. So you can find the initial clustering coefficient right away. So that's going to be just substitute for k equals 8 here, and you will get the initial clustering coefficient. Then what is given is the final clustering coefficient, which is 0.4. So after you go through the rewiring process with the probability beta, the final clustering coefficient is given as 0.4. So the formula for the clustering coefficient as a function of beta is this: the initial clustering coefficient multiplied by 1 minus beta the whole cube. And we know what the initial clustering coefficient is. So this substitute for that 0.4, the final clustering coefficient is the initial clustering coefficient times 1 minus beta the whole cube. So all you have to do is solve for beta. So how can we solve for beta? Just divide this by this. So 0.4 divided by 0.643 is 1 minus beta the whole cube. Then what you can do? You take the cube root, right? So 1 minus beta whole cube is this number. So 1 minus beta is going to be this number raised to 1/3, right? You know how, that's what the math behind it, right? So if a square is 5, what do? You take a square root of 5, which is like 5 over 1 or 2, right? If it's a cube is 5, what is a? 5 raised to 1/3. That's what it means. The math, right? So 1 minus beta is this value raised to 1/3. So you know how to find this number, right? It's a calculator. So 1 minus beta comes to be 0.854. So beta is 0.146. So that is the rewiring probability. Okay? Any question? So let us see. There's one more problem here. Okay, so this is under the enhanced model. So you are given the probability or the weight, okay, for a node of distance 2 edges away from a vertex is given to be 0.2, and for a node which is 4 edges away from a vertex, the weight is 0.08. So what are given is this. This d raised to negative q divided by 2 log n is the weight. So we can call this as a probability just for this problem. It's actually the weight. Okay, because we have to scale it up to really call it as a probability. Okay, so what you are given is a weight. If the distance is 2, the weight is given as 0.4. If the distance is 4, the weight is given as 0.008. It makes sense, right? Because as the distance increases, the weight given to the pair should decrease, right? So given this, and you are given what? The number of nodes is not given. You have to still handle that. So given this information, we need to find the dimensionality, Q. Okay, so how can we handle this? It's going to be again just playing with the formula. So this is like if distance is 2 raised to negative q divided by 2 log n is 0.4. The distance is 4 raised to negative q divided by 2 log n is 0.08. Okay, so just then to get rid of the n or the log n, just divide one by the other, so the log n will cancel out. Okay, so divide this. So if you call this as equation 1 and equation 2, just divide 1 divided by 2. So what will happen? So this is given as 0.2. Okay. So if you divide 1 divided by equation 1 divided by equation 2, you get 0.2 divided by 0.08. What about this side? It's going to be 2 to the power negative q, then the 2 log n and 2 log n will cancel out. Divided by 4 to the negative q. So all you have to now do is simplify this expression and solve for q. Okay? So if you just reverse them, 4 to the power negative q, the denominator will become 4 to the q in the numerator, and this will be like 2 to the q in the denominator. Okay? So this 0.2 divided by 0.08 is 2.5. Okay. So all you have to do is 4 raised to q divided by 2 raised to q is 0.25 or 2.5. So 4 can be written as 2 square. So 2 square raised to q divided by 2 to the q is 2.5. So this is like what? 2 to the power 2q. Okay, so 2 to the power 2q divided by 2 to the q is 2.5. So what is this? 2 to the q is 2.5. So now you can solve for q. How would you solve for q? If you have something like this, q is log 2.5 divided by log 2. Okay, so again, how do I get this? So you are given the distance and the corresponding weight. So substitute for them here. So if the distance is 2 to the power negative q divided by 2 log n is weight 0.2 that is given. Then if distance is 4 to the negative q divided by 2 log n is 0.08. So we want to now solve for q. So just divide the first equation divided by second equation. That will get rid of the 2 log n in the denominator on both. Okay, so clear? That's a math way to kind of find an unknown, right? So 0.2 divided by 0.08 is 2.5, and this is like 2 to the negative q divided by 4 to the negative q. And if you just rearrange them, bring the denominator to the numerator, so it's 4 to the q divided by the numerator is 2 to the negative q, so when it comes to the denominator it's 2 to the q. So 4 to the q can be written as 4 is like 2 square. So 2 square raised to q, and 2 square raised to q, this is like what? 2 to the power of 2q. So 2 to the power of 2q divided by 2 to the q is 2 to the q itself. That is 2.5, and then q is logarithm of 2.5 divided by log of 2. Okay? So you'll get like something like 1.32. So you can leave it like that, even though it's supposed to be like an integer. Clear? Any question? How to solve problems like this? So with that we finish this module. Okay, we also finished the